So here we are back. A uniform thin rod of length 2 meters is supported by an axle on one side. It's dropped from rest from an initial angle of 30 degrees below horizontal. What's the initial angular acceleration and how fast will it be rotating when the rod passes vertical? Now, we already did part A. That was in my previous video. For part B, again, we need to decide what kind of physics we're going to use. Now, if I want to know how fast it's rotating when it passes vertical, that has to do with its velocity, and so I'm going to be using either conservation of energy or conservation of angular momentum. In this situation, conservation of energy makes more sense because we do not have an object that's changing shape and spinning. We have an object that's losing gravitational energy and gaining kinetic energy as it falls or as it rotates, so we're going to use conservation of energy. All right, so let's go ahead and see how that works. So here's all the stuff for part A, but for part B, conservation of energy, we're going to use before and after pictures. So in my before picture, we have a rod that is at 30 degrees. And I'm just going to draw right here on the same picture the after. Let's see, in my initial, the angular velocity is equal to 0 because it starts at rest. And then just right here on this same picture, I'm going to draw the final. And the final is when the rod passes through vertical. And now it has an angular velocity. And we don't know what that is. That's what we're trying to find. And now it's going to be useful to define our coordinate system. And I'm going to be a little bit funny here. I'm going to pick y equals 0 to be up here at my dashed line. And what that means is we start out below 0 and we end up even further below 0. That's okay though. It seems like that's going to be the easiest way to figure out what those heights actually are. So let's go ahead and write our equation. For conservation of energy, we know that the change in kinetic energy, whoops, it's not the way we usually write it. We know that the kinetic energy initial plus the potential energy initial should equal the kinetic energy final plus the potential energy final plus the change in other kinds of energy. And we say to ourselves, what other kinds of energy could there be? Thermal energy, if we ignore air resistance and assume that there's no friction in the hinge, then we can get rid of thermal energy. There's no batteries or electric motors or muscles or anything else that's transferring energy in this system, so we can say that the change in other energy is 0. The initial kinetic energy is 0 because it's not moving. And I think that's it. I think everything else is going to not be 0. The energy we have, the potential energy we have is gravitational. So let's continue to work on this. So we've got mgy initial is equal to 1/2 I omega final squared. Now this is important. This is a rotating object, and the axis of rotation is not moving. The axis of rotation is right here, and the axis of rotation is staying still, which means we can just use I omega squared. If we had something that was both rotating and moving through space, then we would have to use 1/2 I omega squared plus 1/2 mv squared, and we would use our axis of rotation as the center of the object. However, if we have an object that's rotating so that the axis of rotation is staying stationary, then the kinetic energy is just 1/2 I omega squared. Okay, plus mgy final. So that's all well and good. now I've got a little bit of an interesting geometry problem to try to figure out the initial and final height of this rod. And it's very important that we measure the height to the center of the rod. We always measure to the center of mass of the object. So I need to figure out how high the center of mass is. So what I'm going to do here is imagine a little triangle. And the hypotenuse of that triangle is L over 2. And this side of the triangle is my y initial. Actually, the y initial is negative. That's how far below 0 it is. Well, that's not too hard to figure out. That side of the triangle is the opposite side, so that's the sine. So this gives me mg times negative L over 2 sine of 30 degrees. Okay, and that's equal to 1/2 I, we looked that up in the previous problem, it's 1/3 ml squared. That's for a thin rod rotating around one edge, omega squared, plus mg y final, and the final y is half the length of the rod below 0, so this is equal to negative L over 2. All right, so here's our equation. Let's see what we can do with it. It ought to simplify some. We have minus mgl sine of 30 degrees over 2 is equal to ml squared over 6 omega final squared plus mgl over 2. Seems like the first thing to do is to divide everything by mass. Next thing might be to divide everything by L. One of my L's cancels. Next thing might be to multiply everything by 2. I would get rid of that and turn that into a 3 and get rid of that. Well, let's see where that leaves us. Minus g sine 30 equals L over 3 omega final squared. I seem to have missed a minus sign. Minus g. See, I had a minus sign here, and I didn't have a minus sign there. And so that was an algebra mistake, but I caught it, luckily. All right. Still needing to get down to finding omega. So I'm going to add g to both sides, and I get g minus g sine theta. Added g to both sides was equal to L over 3 omega final squared. So finally I get omega final is equal to the square root of g minus g sine 30 divided by L over 3. All right, so let's see if I can plug that into my calculator. 9.81 minus 9.81 times sine of 30 is 1/2, so I'm going to go ahead and plug that in. I'm not going to use my sine function on my calculator. Divided by Length is 2, so I got 2.71 radians per second. Angular velocities, when we do everything right, are measured in radians per second. Angular accelerations, when we do everything right, are measured in radians per second squared. Okay, so that was a conservation of energy problem. And to do this, we said that the initial kinetic plus initial potential was equal to final kinetic plus final potential plus the change in other kinds of energy. And the new thing, the new thing we had to do this week was say that kinetic energy of a rotating object is 1/2 times moment of inertia times angular velocity squared. Other than that, it's just like a conservation of energy problem from a couple of weeks ago.